Yeah, what I want to introduce is what I call ready, fire, aim. Right, it's a simplified approach to rapid root cause analysis, and the whole idea is to create action. Right, ready, fire, aim is more so, hey, got a general direction, take action, and then readjust if needed. But the whole point is creating action. So what we're going to go through is just talk about a need for rapid root cause analysis and why it's come up. Key steps and tools that we can use, and a worked example. And as I mentioned before, I'll have a little Q&A. Now, I will, as a caveat, right, this isn't the only way to solve problems, right? Very often, there's a myriad of tools and methodologies, but I've found that this is definitely one method that is pretty ubiquitous and can be applied to many types of issues and problems. And for those of you in the industry familiar with CAPA, corrective action, preventive action, right? It's a formal process for solving problems in many industries. Some required by regulatory regulations, requirements, and but at the end of the day, it just makes good sense, right? To have the structured approach to solving problems. Right now, the issue is some of them are very slow moving, right? It takes forever to get some of these over the board, despite the fact that organizations have metrics and such to get a CAPA done in 30, 60, 90 days, what have you. It's not always the case. And I've been in some organizations where we've seen some CAPAs, we joke around, are ready to go to kindergarten, right? 5-year-old CAPAs and such. And it shouldn't take that long to solve problems from time to time. Now, some of them are, and I get that, but not always the case. So what causes that? And this isn't the only cause, but a lot of times I find is that engineers or teams get stuck, whether it's CAPA, non-conformance, or just some issue on the production floor, this analysis paralysis, where by definition, right, it's the inability to make decisions or progress due to overthinking of a problem. And that could be caused by having too much information or too much data at hand, or the improper selection of tools. You go to a root cause analysis training and you get a myriad of tools thrown at you, and you're trying to use them all, or you're not using them correctly, right? So it's misuse sometimes of these common tools. And what that does is it results in a slow, ineffective problem resolution. And why is that a problem? It allows additional time for a problem to perpetuate. It increases your risk. And the longer a problem takes to get resolved, thinking like a detective, the scent grows cold, right? If it takes a long time to get to root cause, you may never get there because the objective that you need just goes away. So what can we do about that? Rapid fire action. So I mentioned before, ready. Right? That's by definition, right? Ready. It's being in a suitable state for an activity, action, or situation. It's being fully prepared, right? So before you embark upon your root cause investigation, you want to make sure that you have that foundation ready and set. Next is fire, right? Which is a verb. Right? I told you we're going to be looking to make action. Fire is to propel with force and velocity, and I'm highlighting that word for a reason. You see, to discharge or let fly an object. Then from there, we can readjust, right? Now we got action going. We can readjust if needed, and aim means to point or direct towards a specified object or goal. The key is to act, right? And it's creating action, motion, right? Not just thinking, but action with velocity. And the difference between velocity and speed, velocity has both direction and magnitude, right? So it's fast, but it's directed fast. So it's meant to be, specified like laser sharp focus right towards the stated goal and objective. That's kind of the philosophy behind it. And with it, there are 5 or 6 steps. I forget the exact number, but we're going to go through them. And these are steps that I find extremely helpful in many situations. Again, it's not necessary for all of them, but I guarantee if you at least start off with these, it'll be a good start towards any root cause investigation that you need to do. The first thing that I like to do, even before a problem statement, is issue characterization. I like to understand what type of issue that we have at hand. And there are three that we've defined. The first one is a sudden change. This is where you're running along at a certain performance level and you get a rapid drop in performance, right? So as you can see by this chart, we're running along on average about 95, hypothetical number, right? And then all of a sudden it drops down on average 80. And it's sustaining there. We don't know why yet, right? But we know that this is a sudden change type issue. The second one is a steady decline. This is where, once again, you're riding along at some steady state, and it didn't quite sharply drop off, but it slowly starts reducing over time in performance. May or may not eventually flatten out. It may continue going down. In this particular example, we're showing flatten out, but this is a steady decline. So it's slightly different from the sudden change, right? There was an event that maybe triggered it, but one happened abruptly where it was catastrophic, and the other one took a little while to have a wearing effect. And the last one is a performance gap. This is a type of issue where these come up in audits and things of that nature, where we were always there, right? It's not that something changed or anything like that. It's just that we're always operating at some level of performance lower than some other level that we would like to or should be operating at. Knowing the type of issue helps us direct the investigation approach as well. There are clues in each one of these that can kind of give you that idea. And again, I like looking at these before we even put the problem statement together, because this could even influence how we state the problem. Then next is the problem statement. So putting together a good problem statement, and anybody who's been through any kind of root cause analysis training, this isn't going to be new. 4 W's and 1 H. I've seen other variations, 5 W's, 2 H's. I tend to be more lean. And I think that you'll see in the example that we have later on, this is generally sufficient. And why do we want to do a good problem statement? First and foremost, we want to clearly state the problem. I think it was Einstein said it best: a problem that is a problem that is well stated is half solved. And we want to make sure that as we're going through our investigation process, we can always go back to the problem statement to ground ourselves and make sure that we're chasing the original problem that we intended to. And then you find out at the end, when we do put in a solution, if we want to demonstrate the effectiveness, we want to be able to tie back to the original problem statement to show that we've in effect resolved that original issue. So the 4 W's and the 1 H, it's what was the issue, who identified it, where was it identified, when was it identified, and how much or how many were impacted. And then even with these, and I'll glass through these, I believe the slides will be made available as well. But when you are defining what the issue is, this is the actual failure mode, right? So you want to consider the failure mode, why it's an issue, and the type of issue it is, as I mentioned before. Is this a sudden drop, steady decline, or a performance gap? By including who identified the issue, it provides us with an eyewitness that we can, right, the first person that we can check in with. But it can also provide additional insight to aid in the investigation. But knowing who did it, understanding their role, what they would normally be doing, helps aid our investigation as well. Where it was identified, you want to consider when I talk about where, it could be a physical location where, it could be a location, if we're talking about defect, it could be a location on the part or on the component. Or it could be a location within the process, right? So, how you use that where depends on the situation. And more information you could put in there while still being concise, it'll be very helpful in guiding the investigation. When it comes to when, Timing is everything and could provide clues in the investigation. So consider when, as far as dates, times, shift, or even when in the process, very similar to where. And then for how much and how many, we want to identify the number of impacted items or the frequency of the recurrence. And you'll see in the example that we have a good example on that on frequency. This will help us determine the level of urgency as well as some additional insights to resolving the issue. So the idea is, and again, we'll see in template form, just very concise, briefly answer the questions with known facts, and then we're going to stitch them together to form a concise problem statement. Once we have the problem statement, and again, if this is a team-based event and you're physically with them, write it down, make it visible so that everybody can see, and we're all having the same compass, facing the same direction to resolving the same issue. The next thing is the sequence of events, right? What were the steps that occurred that led up to this being an issue, or this being identified as an issue? This is different from a process map. I mean, there may be elements of process mapping that may be in here, but this is more so on the continuum of time. What was the sequence of events? What were the events, the things that had happened that led us to us stating this being an issue today? It does look like a process map when you lay this out, but again, there is a slight variation from that. When you are doing your sequence of events, there are some do's and don'ts that you want to consider. Certainly you do want to focus on the facts of the issues. You do want to focus on events that occurred, right? So happenings. Those are potential triggers and clues. You want to maintain a high-level view. Very often I've seen this, especially when teams try to do process mapping. They'll fill a wall full with sticky notes, or if they're doing it in Visio, there's you have to zoom in because there's so many little blocks and such, and it becomes so complicated. You lose purpose of the tool, and it's very difficult to kind of like focus in on and now there is time when you want to drill down, and we'll show that in the example. But your first pass sequence events, keep it high level. You can always add more detail afterwards, and then highlight on focusing on key events, that kind of stepping stone that defines how you went from point A to point B. The things you don't want to do, right? So if you're focusing on facts of the issue, then we do not want to speculate at this point on potential causes or solutions, right? We don't want to introduce any bias. We just want to, right, like a detective, just the facts, and what were the sequence of events that led us to where we are. Don't map, as I mentioned before, don't map the entire process, right? Just keep it high level. We can add detail later if we need to. Similarly, don't dive too deep down the rabbit hole, right? Those are paralysis analysis, diving down the rabbit hole, wrapped around the axle, right? These are all terms that we've heard when folks get stuck and we overanalyze. It slows down the process and it prevents us from moving forward and creating action. And don't consider each and every event suspect, right? Just because you're not trying to think about what are all the events that may be suspect. Similarly, you're not trying to map the whole thing. Just let it flow, right? Let it flow. Sequence of events. What were the things that had happened that brought us to where we are today? And then the next step, we'll see. We'll add a layer of potential causes from there. Once we have that sequence of events, and we've highlighted some of the areas that we want to focus in on, next thing we're going to want to do is know why these certain outcomes were produced. Okay, and the most popular tool that most teams will resort to, and there hasn't been a client that I've been to that didn't have this tool in their CAPA process or their NCMRs, would be the 5 whys, right? Naturally. However, I'm going to caution against the 5 whys, and I'm going to advocate and again, a lean version of fault tree analysis instead. But why not 5 whys, right? It's a very easy approach, and it's very easy to teach somebody how to do 5 whys. Why would we not promote that first and foremost? What I found is that it's when you're doing 5 whys, it's very linear, and it only creates a single path, right? So it doesn't necessarily take into consideration conditional events, right? So if you could have, this occurred because these two things together occurred, it's possible to put that in 5 whys, but fault tree analysis is a much more powerful tool in visualizing that and exploring that further. And unfortunately, right, and if you've been on enough CAPAs, especially some of the higher level ones, the path can be forced, and it's sometimes intentionally, sometimes unintentionally. They'll never admit to the intentional one, but I have sat in more meetings than I've liked when a leadership team says, "Hey, we wanted to say this in the end. How do you get the 5 whys to fit it?" And it's at that point, there's no value in the tool anymore, right? The bias is already there, and they're just looking for a story to get you there and using a tool. If you want to keep true to the process, let the process and let the tool itself guide us to appropriate root cause. Hence, fault tree analysis, it is naturally event driven, so it goes hand in hand with the sequence of events that we introduced before, because you already have some events, and now we want to talk about, okay, well, what led to those events? We may use some 5 why questioning. So it's, I still see value in that, but I think the fault tree analysis is a little bit stronger, because as we drill down when we do 5 whys, we can also go across, right? So we can go across, go down. You have that 2 dimensions that you could do in the fault tree that you can't quite do with 5 whys alone. And the other nuance, and I've seen this both ways, my personal preference is having the arrows pointing up, towards, from the causes down at the bottom all the way up to that to the issue event up at the top. Reason being, it is a gentle reminder of that cause and effect relationship, right? So when you're going from the bottom up, those are causes that cause certain effects, and the arrow again is kind of that sequence of time, if you will. I should note, for those that are not familiar with the fault tree analysis, and we'll see this in the example as well, but the symbols that you see here, there are 4 different symbols. One, first and foremost, is a rectangle. That's that's an event. So that's an event that occurred, and we want to understand what led to that event. Just below that top, just below the top one, we have this. The shape, it's a logic gate to represent OR, and it's indicative of kind of the rounded top with on the bottom, it's got like a little arch. And that OR gate is basically, it's a conditional OR, meaning that either A or B could occur and cause the outcome event, right? So it's either or. Below that, you'll see another gate that's got the rounded top with the flat bottom. Those are AND gates, and that is where you have 2 events coming in or more with the conditional AND, meaning that this and this have to happen. So, for example, if I want to know, if I want to understand how did I get wet, because when I went outside, it would have to be raining, and I would have to forget my umbrella. Right? Those 2 things both would have had to have happened for me to have gotten wet. If one of those things didn't happen, I wouldn't get wet. So that's kind of where the conditional AND comes in. And the last symbol on the diagram is a circle. Those are the basic events, right? Those are the things that, and again, I think if you dig deep enough, you could find something else that caused those. But those are usually the basic events. Those are things that root cause analysis terms, right, we would call potential causes, contributing causes, likely causes. We don't know if they're root cause yet until we've proven them in or out. But those are the causes that we would be looking to assess that maybe we can, if we do determine them to be root causes or contributing causes, we can determine appropriate corrective actions to address those to prevent the other events from happening. So it's almost like going back in time, right? It's going back in time to address the primary event from cascading into a future of an undesirable event. Once we have that, and we have those causes, if you will, we'll want a mechanism to determine, right? Because the fault tree analysis, it could branch out quite a bit. We'll want a mechanism to help rule things in or out. And this is where we use a what we call is not analysis. And here too, it's for those of you who work in the industry and are familiar with root cause analysis tools, whether through training or your CAPA process, what have you, you may have seen a version of this. Usually you'll see the is not to the left. We put it on the right. The reason why is we want to start with the causes. We want to determine what type of review or what kind of test, what kind of data can I collect and look at to either determine if my potential cause is or is not a root or a contributing cause. And then we leave this template open to collect the outcome. So a lot of times what happens is we'll put all the potential causes that we want to explore. As a team, we'll come up with, okay, and again, this isn't an all-day affair or a week-long event. This is, here are the things we want to explore. What data can we use to support it, either in or out? And we'll come up with a strategy. We'll assign those tasks to individuals to go explore, and then we ask them to come back with their outcome along with some objective evidence. And we'll want to record that in a table. And objectively, based on the outcome or the evidence and the supporting evidence, we would then make a determination. Is this a root or contributing cause, or is it not? And we fill out this grid to document that. So we list all the causes from the fault tree analysis. We determine the appropriate tests, conduct the review, document the outcome with evidence, and then make our determination. So again, this is more so, this isn't full problem solving. This is more of the root cause analysis. So the process technically ends here once we have the is not. It is appropriate, right? I mean, these are just tools, so they're meant to facilitate the process and to create a record, but it's not the record in and of itself. You still have to put a story together. But the beauty of keeping it simple and using a handful of tools that are, that work well together like this, right? They naturally fit together like pieces of a puzzle. It allows you in your write-up, in your investigation write-up, whether it's a CAPA record, NCMR record, complaint file, you tell the story from top down, right? You basically say, hey, we determined it was this type of issue. There's a problem statement. We did the sequence of events, identified these areas where it could have been detected or could have been caused, did a fault tree analysis, came up with these conclusions. We reviewed this data, we did this test, we did whatever, came up with these conclusions. Here's our root cause. And then we would go on to how we would seek to resolve that. So that's the methodology. I think I have an example coming up, but before I do, certainly like to open it up for any questions that you may have on the process before I go into the example. I'll give a moment.
More comfortable unmuting and just asking the question, feel free.
Oh, perfect, thank you. All right, well, we'll go ahead and continue. And maybe after seeing an example, it might trigger something else. And like I said, got open time at the end here for question, answer, and any discussion. So here's a common example. Manufacturing can't meet customer demand due to frequent equipment issues. Okay, somewhat vague, right? But a production manager, production supervisor may come across with this complaint. So what do? Right? First and foremost, we want to understand what type of issue it is, right? And in this particular example that we worked through, and this is a real example that we're using here. That this chart isn't real data, but it's a very real example where it was always an existing issue. It wasn't something that happened all of a sudden. It wasn't something that degraded all of a sudden. This was a pain that from the day that this was released into production, this was a pain that that this production leader was dealing with on a daily basis. So now that we know the type of issue, what do? The problem statement. And again, we normally do this like this, right? I'll pull teams of people together and we'll just sketch this up on a board, and it's literally a couple bullet points. This is a few minute exercise. What was the issue, right? We're talking to the people, we're talking to the supervisor, we're talking to the technician, the operators. Well, we're missing our production output, and we have this, in somewhat of a cause, right? But it's an issue in and of itself. I have excessive welder downtime, right? So the downtime is really the issue. That's why is it an issue? Because it's preventing me from hitting my production goals. Who identified it? Production supervisor came forth with this one because they're always on the hook for getting production output. To protect the innocent, right? I'm not going to disclose the company nor the product because you might be able to make the connection, the company, but we're just going to call it the XYZ production line. This happened on a daily basis. Actually, it was every shift they were having this issue. Some shifts worse than others. And on average, it was about 1 hour downtime per shift. So again, those are just a couple of brief facts that we collected from the team, from the folks that were feeling the pain, and we stitched that together into a single concise problem statement. The XYZ production line supervisor claims the daily production goal cannot be met due to, on average, 1 hour of welder downtime each shift. If you look at that, concise statement has all the facts that we've collected up above and gives us a good understanding of the issue that we have at hand. Now, with this said, there's two ways to do this if you're already thinking about it, right? The quantity that we put in here was the 1 hour shift, right? We could have put the quantity in production output as well. That's certainly another option. And when we did demonstrate in the end, when we did demonstrate the effectiveness, that was the number we used because that's a metric that they look at daily. But we, for this particular example, we focused in on the 1 hour because that's what we really wanted to get down to. We wanted to either, eliminate or at least reduce that 1 hour significantly, knowing that every minute that we would give back to production, they would be able to produce more units. So sequence of events, and this is an example where I mentioned you start off very high level and then you could drill down where you need to. So, and again, this is you're also going to see why this is different from a process map. At the top, we're talking about the production supervisor complaining that on a shift basis. On a shift basis, they get to the end of the shift and they're short units. Right? So we're starting at the end of shift. That's where we detected the issue. We detect the issue at the end of each and every shift. So what happened? Well, we don't have to go into the full production line, right? So we know some production steps happen, but somewhere in the middle, the welding operation happened. Since we know that that's an issue, we broke that one out. Worked that backwards. There were some other production steps that happened, and then we began shift, right? That maps out a day, right? So on a given day where we know that we're feeling this pain, we began the shift, we did some production steps, we got to that terrible welding operation, right? And then once we did get through that, right, we had some additional steps, we get to the end of the shift and we're short units. So what happens here, right? We break this out. this kind of fans out into a sub-process. Well, at our welding operation, we would then identify a bad weld. Once we had a bad weld identified, and this is what it would look like. The operator would raise their hand and call the technician over, and the technician would then go on to disassemble the machine, right? They would remove the safety shield that was protecting the assembler, the machine operator from the electrodes. They would then go on to replace the electrodes, align the electrodes, replace the shield, and then return to service so that they can continue their welding operation and pass the units on. So it was this loop that we knew that we were losing an hour on average, we had an hour of downtime, lost production time per shift. It's terrible. The highlighting that you see here, and we didn't necessarily have it in the method, but here in this example, we like to highlight where we detect the issue. We don't have one in this case, but if there was, where did you fail to detect the issue, right? So if there was an opportunity at an inspection point that maybe a failure got through, we would want to highlight that too, because we'd want to understand why did it get through one of our controls. But then we also want to understand where the potential causes are, right? If we're detecting it here, what happened prior? And again, this is the value of a sequence of events, because if you think about a continuum of time, if you have a problem now, it had to have been caused sometime before, right? And if you were to do a full process map, you'll see that things happened afterwards, but that's not suspect because I'm detecting it here. So since I'm detecting it here, I want to look back. And what we found is with this particular case, there were two types of problems that led to 1 hour, right? How do you get 1 hour of downtime? Well, you get frequent breakdowns, right? So for every time it breaks down, that slows down and I lose production time. But then you also have the duration of the downtime, where the machine is being worked on. So we highlighted those as either a frequency contributor or a duration contributor. Right? So if there's a failure at the welding operation, that contributes to the frequency. For each and every failure, that's lost time. The bad weld identified. Right? So every time the operator stops and raises their hand, that's time. Now, where we were really losing the time is when the technician would totally disassemble the part. So removing the shield took quite a bit of time. Replacing the electrodes, not so much, right? So this is where we're not indicting everything. The alignment process was pretty lengthy, and then putting the shield back together. So now we have this sequence of events. We have a good story that everybody is able to look at, and now kind of gun in with laser sharp focus, but using fault tree analysis to kind of get to the bottom of it. So starting at that top event, 1 hour downtime per shift, right? That's the event that we're trying to prevent, right? So what are the things that happen? So the downtime event, the frequency, and the duration, right? Those are anded together. It's both the frequency and the duration that was eating our lunch day in and day out. So we and those together, and then from there we drill down one branch at a time. So when we get down and say, okay, we had a downtime event. Why did we have a downtime event? And there are a couple of reasons, but the most prominent ones were, well, we truly have an off-center weld. Right? So this was a coil, and we were looking to do 90-degree welds, and sometimes they were off-center. And then other times they were just cosmetic. Right? We call it a false alarm, alpha error. And these are ones where the assemblers were just, the machine operators were subjectively saying, hey, I don't like the way this one moves. So what caused those, right? Well, so off center is not a basic event, and having this cosmetic thing isn't necessarily a basic event. What caused those? And here we could see on the off center weld, we had this off center rotation. When you're doing 90-degree welds on a coil, as you rotate, there was a channel, and what was happening is this thing was flipping out of the channel. So it was no longer aligned with the electrodes. So we had this off-center axis that we knew was a primary cause that we needed to address. And then when it came to the machine operators, right, using their discretion, we found out that there was no true visual standard that was provided to tell them how to discern between, good and bad, conforming and non-conforming product. So that's down the frequency side. On the and this would be more on the inherent in the equipment or the assembler. On the long repair time, this is also going to be a combination of the interaction, if you will, the design of the equipment as well as the technician, right, working. So why were the downtimes taking so long? Well, these could have been one of two things, right? The shield assembly and disassembly was definitely contributors, right? We had this protective shield, and the time I take disassembling the shield, I'm not really fixing the machine at this point, right? I'm not addressing the electrode issue. I'm just taking something apart. So from a lean perspective, it's non-value add. Same thing for putting it back together. It's important. We need it to be there, right, to protect, the safety of the machine operator, but it's not necessarily important to the inherent function of the machine. And it was just complex shield design. It was a 3-piece shield, Lexan, and the whole thing was screwed together, and it was very time consuming to take apart. The other path is the electrode alignment, not necessarily the replacement, but the alignment. And when we observed the technician doing the job, what we found out was there's an alignment tool, just wasn't using it. When I asked, why aren't you using the tool? He said, well, in his words, it was the electrode doesn't fit anymore, right? Or the tool doesn't fit anymore. That puzzled me, but long story short, it turns out that the electrodes were coming in slightly elliptical and didn't fit in the round aperture of the alignment tool. So anyway, this is where we got to, right? We kind of drilled down. And one thing I want to point out here too, right? We can have a discussion, is this or is this and? Just giving you a little insight of use and application of the tool. We chose or in this case because these are two independent events, right? The shield assembly and disassembly, the time that I take there has nothing to do with the electrode alignment, right? They are independent, meaning that if I didn't have to do electrode alignment and I just had to maybe do a cleaning or what have you, I still had to disassemble the shield. So I'll still lose time here, even if I'm not losing time here. So they are independent, and it could be one or the other. Oftentimes it was both. So those were the conclusions that we drew. And but just to document it and tell the whole story, right? And again, we're trying to reduce the hour, so we really wanted to make sure we're going after the right things if we were going to make any changes. For the off-axis rotation, we observed the process, right? It was something that, somebody said that it could happen. We weren't sure how often, but when we looked at it from an engineering perspective, it happened. And it happened a lot more often than we were surprised how many good units that we were able to get off as often as was going through. So that was confirmed. Next was no visual standard. So we performed a measurement method analysis, right? So again, that's a hypothesis. We said, okay, you don't have a procedure, but does that really lead to us having all that variation? So we took a couple assemblers, we gave them some conforming parts, non-conforming parts, and sure enough, they were not consistent. Now, they did tend to take the more conservative approach. So thinking about patient safety and stuff like that, that was great. But from a manufacturing standpoint, a lot of alpha error and and inconsistency. So yes, not having a visual standard was definitely a contributing factor to the frequency of the issue. The complex shield design, we timed it, and yeah, it took 15-20 minutes at best to disassemble and then try to reassemble it again. So that was definitely a major contributor in the duration part of our downtime impact. And then the elliptical electrodes, here we wanted to do a couple things, right? We wanted to measure the electrodes to see, right, if are they truly out of round? Are they in spec? Right? Do we have a sourcing issue? What do we have here? So we wanted to measure the electrode. Same thing with the alignment tool. We wanted to measure the alignment tool, or at least the critical feature, and then we wanted to compare it to their respective drawings. We wanted to see if we had a specification issue or was it a tolerance stack-up issue. So what we found was, yes, indeed, electrodes are out of round. However, they were in specification. They were within tolerance. Same thing with the alignment tool. The drawing was within tolerance. However, there was still a little, so they were within specification, but there was still margin within the tolerance of the drawing to fit the electrodes as they're. So, but either way, we said that, yes, that is still that's still a contributor, right? It's at the end of the day, that was an issue that prevented us from using the tool that would expedite the alignment process. So that's it. I mean, for root cause analysis, that's it. I did throw in a bonus here because, since this was a real example, I didn't want to leave our guests hanging as far as, well, what'd you do next? This is another tool that we like to use following root cause analysis, especially when you have multiple causes and you need to implement multiple solutions. It's very difficult sometimes to map that out, especially if you're trying to write that up in in text form, in paragraph form for your CAPA or NCMR. So we advocate using a matrix like this. You can use it as an attachment or as a figure within your write-up, but starting with this and then doing the write-up, following this is much more helpful. So at the top, we had those root causes, contributing causes, right? Off-axis rotation, no visual standard, complex shield design, and elliptical electrodes, right? So those were the causes that we were gunning after. And we identified 5 action items that we wanted to pursue. The first was to design a cover plate that would go over the channel so that the coil would be constrained within the channel, would not come out, and would stay aligned with the electrodes to receive the weld. That solution would directly address the off-axis rotation in and of itself. Wouldn't need to do anything else after that. The engineering downtime, so we decided in the interim, until we can sort out this visual standard, the operator, before they called the technician over to disassemble the machine and start surgery, we'd have to get engineering judgment first. So manufacturing engineer would have to come over first and make the assessment. Is that a conforming product or is it non-conforming? And I could tell you right now, I got called in on a few of them, and I still remember when technician fixed the machine and called me over because he spent about 2 hours on it. It was a tough one. And the machine operator, he said, okay, go ahead and test the unit. Machine operator went ahead and he ran the first unit, threw his hands up in the air, and he's like, see that? And I said, what's wrong with it? He said, well, it's ugly. It's like, okay, show me in your procedure where we reject for ugly, right? And it wasn't a hideous ugly or anything like that. Right? It was a cosmetic thing, but it meant the intent of the design. The coil itself was welded and things of that nature. So it was very apparent that we needed that first level of interaction before, while we were in parallel working on the longer term project of implementing a visual standard that everybody would be, that the method would be validated and we would train them to. So in the interim, we would, engineers would get called to the line to help calibrate a little bit, or at least make, proper judgment call. And if we should, take the machine down or allow production to continue. That was an interim action to address the idea of no visual standard. But then creating that visual standard, as I mentioned before, validating it with a statistical based sample size, and training everybody and maintaining that their qualification was going to be the long-term solution for that. For the complex shield design, we had this engineer. He came up with a great idea, and he said, "Hey, instead of disassembling it, why don't we just put the thing on slides? Put a little thumb screw on the side. We could slide it up out of the way, slide it down." So he came up with the design. We ended up implementing it, made the change, did the installation qualification, made sure it still provided the same level of safety. But what took 15, 20 minutes at best at both ends, so maybe sometimes a half hour just in shield management, it was seconds, right? So significant improvement, there. And then last but not least, on the with the elliptical electrode, it was within specification. So it's not that there was anything we could do about it. It was a tolerant stack up thing. But the easiest thing we were able to do that day was bring the tool down to the machine shop with the drawing and ask them to open up the hole ever so slightly so that it can accommodate the electrodes that we have, but still maintain compliance to our drawing. There's no change whatsoever. Right? It's just more of a adaptive machining, if you will, to meet the needs of the current situation. So that was our solution to addressing the elliptical electrodes. And that concludes the discussion. That concludes the need, right, for rapid root cause analysis. I more recently I had actually a team of engineers, manufacturing engineers, quality engineers that were faced with a backlog of NCMRs, and they were overwhelmed. And I pulled them all into a workshop like this, and we used their examples. And while I said up front that this isn't necessarily the panacea that's going to solve every problem, this approach actually worked for every single one of their NCMRs, right? So they were very thankful because now they had a standard approach to where they can kind of fill in the blanks, and it made their write-ups that much easier too, because by using these tools and then using the tools to kind of quickly get to root cause and appropriate actions, it also helped facilitate a standard way of writing up the record that was required for their process as well. So definitely a need, definitely a lot of value. I hope that you'll see maybe connection where you work as well. We introduced the key steps and tools, and I gave you a very real example that we worked through to help one area that had that 1 hour downtime, and they pretty much recovered all of it. The downtime afterwards was it was a lot less frequent, and certainly the duration wasn't there. So do the math. 1 hour out of an 8-hour shift, right? We gave them back about 12% of production capacity just by using these tools and putting in some real targeted fixes.